Hello everyone. So welcome to the fourth hour of optics. In this hour, we are going to talk about refraction from the curved surface. And once we have completed refraction from the curved surface, we will talk about lenses. If we won't be able to complete lenses in this hour, we will take them forward in the next hour because prism take comparatively lesser amount of time and question comes from lenses the most. So without wasting time, let's start this hour. So, in the last hour, towards the very end, we learned this thing that let's say you have got this case that a ray of light is moving parallel in the rarer medium. It tries to enter into denser medium and the surface here is curved. And I asked you a question, once these rays enter into the denser medium, they will get converged or diverged. To understand that they will get converged or diverged, think of the normal at the points of refraction. So if you visualize the normals at the point of refraction, they will be something like this. As the ray of light is moving from rarer medium into denser medium, they will bend towards the normal. And as these rays of light will bend towards the normal, you will say that these rays of light are getting diverged. Then we talked about three more cases. The second case, the ray of light is moving in denser medium and it tries to move from denser medium to the rarer medium, but the interface is curved. So when the rays move into rarer medium, they are converged or diverged. So we will again think of the normal. And as we know that the light ray is moving from denser medium into rarer medium, the light ray will bend away from the normal. So these rays after coming out will converge. Then we took the third case and then we took this fourth case. So this has been discussed already toward the very end of the last hour. Now sir, why have you started this hour with the same thing that we have learned in the last hour? Because we need to understand something about biconvex lens and biconcave lens. Let's say you have a biconvex lens. And let's say this biconvex lens is made up of material having refractive index greater than the refractive index of the surrounding. So when rays of light hit its left surface, tell me, will they get converged or will they get diverged? So you will say that, sir, if we just look on the left surface, to the left of the left surface, the medium is rarer. To the right of the left surface, the medium is denser. It's the lens. So you will say that this is the same case as the case 3. So the rays will get converged. Now, once converged, when these rays reach the second surface, now these rays are moving in the denser medium and they're trying to move from denser medium into rarer medium, and the curvature looks like this, which is the same as in case 2. So the rays will get converged again. So do understand that in the normal biconvex lens, which is made up of glass, when used in air, both the surface converges. Similarly, if you have a biconcave lens, let's say made up of glass, which has got refractive index of 3/2, placed in surrounding air, when rays of light hits its left surface, will the left surface converge or diverge? So this case is same as case 1. The rays are moving in rarer medium. The surface curvature is like in case 1 and they are trying to get into denser medium. So the rays will be diverged. Now, once these rays have been diverged, when they reach the second surface, tell me, they will get converged, they will get diverged again, or they will move straight. So you will say that, sir, when these rays reach the second surface, they are traveling inside glass, they are traveling inside denser medium. And the curvature looks as if in the case 4. So when these rays come out, they will diverge further as in the case 4. So in case of biconcave lens, both the surfaces diverges. We will talk more about lens, but first we need to tackle refraction on curved surface. So we need to understand the formula for refraction on curved surface. And I know that many of you do not even remember this formula. So let's say you have got this curved surface. And here you can see we have placed rarer medium, here you have got denser medium. And let's say here is the object and here is the image formed. Now, just like the cases we have learned already, Here also you have to take care of two things. When I taught you the mirror formula, I said that 1 by V plus 1 by U equals to 1 by F. You need to remember the formula, and you need to remember what is the meaning of V, what is the meaning of U, what is the meaning of F. Here V is the position of image with respect to pole. Everything is measured from pole. Here U is the position of object with respect to pole, and F is the position of focus with respect to pole, right? So first of all, what we need to do here is we need to mug up the formula. So the formula goes like mu2 by V minus mu1 by U equals to mu2 minus mu1 by R. Mug it up. Mu2 by V minus mu1 by U equals to mu2 minus mu1 by R. Mu2 by V minus mu1 by U equals to mu2 minus mu1 by R. Mu2 by V minus mu1 by U equals to mu2 minus mu1 by R. You need to mug this up. And once you have mugged up this formula, then you need to understand very beautifully what is the meaning of mu2, what is the meaning of mu1, what is the meaning of V, what is the meaning of U, and what is the meaning of R. Now beta, first of all, we will talk about refractive indexes. What is the meaning of mu1, what is the meaning of mu2? So we say that mu1 is the refractive index of the medium containing the incident ray. Mu1 is the refractive index of the medium containing the incident rays. If you have got object placed here, then rays will come out of the object and they will hit the curved surface and will get refracted from this curved surface. If here I ask you what is mu1, you will say that, sir, mu1 is the refractive index of the medium containing the incident ray. Similarly, what is mu2? Mu2 is the refractive index of the medium containing the refracted rays. Mu2 is the refractive index of the medium containing the refracted rays. So here, once the rays have came out, since we have assumed this to be rarer, this to be denser, and this is like the left surface of the equi-convex lens. So you know that these rays will get converged and they will meet somewhere here, and here is where we have placed the image I. So what is mu2? Refractive index of the medium containing the refracted rays. Next thing, beta, what is U, what is V, what is R? Listen to them carefully. Here you know that the refraction takes place on this part of surface. The center of this curved part on the surface is called the pole, just like we use the term pole for our spherical mirrors. So we say that what is U? U is the position of object with respect to pole, not distance, position. And when we are talking about position, we need to know which direction has to be taken as positive, which direction has to be taken as negative. The direction of motion of incident ray is taken as the positive direction. You again take pole as the origin, and the direction in the direction of incident ray as positive direction, and the direction in direction opposite to the incident ray as the negative direction. So this is important. So what is U? Position of object with respect to pole, not distance of the object with respect to pole. No, position of object with respect to pole. Next term, what is V? V is the position of image with respect to pole. So U is position of object with respect to pole. V is the position of image with respect to pole. Now when I ask the Janta of this country what is R, all of them say, sir, radius of this curved surface. No. If you take R as the radius of the curved surface, you won't get the answer. So you need to understand the definition of R. R is the position of center of the curved surface with respect to pole. So for this curved surface, the center will be somewhere here. The direction of incident ray towards right. So you will say that the position of center of this curved surface with respect to pole will be positive. So what is R? Position of center of the curved surface with respect to pole. You need to understand this definition clearly. Now moving on and talking about transverse magnification. What is the magnification in the case of refraction from a curved surface? So let's say we have got this case, and here we have placed an object. This is the pole, and let's say the image is formed here. We can find out the position of image using the formula mu2 by V minus mu1 by U equals to mu2 minus mu1 by R. But what will be the magnification? So the magnification formula goes like M equals to V by mu2 upon u by mu1. And do understand that here you must substitute v and u with sign, v and u with sign. Sir, do we have to substitute mu1 and mu2 with sign as well? They do not have any sign. Mu1 and mu2 represent refractive index. They are always positive, right? So here you need to substitute v and u with sign. And the magnification is v by mu2. The image is in the second medium. Upon u by mu1, the object is in the first medium. You can remember it this way. If a medium has a thickness t and have refractive index mu, then as seen by someone in air, the thickness doesn't appear to be t. The thickness appear to be t by mu. So the magnification is nothing but v by mu2 upon u by mu1. So now let's see a problem to understand how to use the formula. In a thin spherical fish bowl of radius 10 centimeter filled with water of refractive index 4/3, there is a small fish at a distance of 4 centimeter from the center C as shown in figure. Where is the figure? Here is the figure. So the fish is at a distance of 4 centimeter from the center C. Where will the image of the fish appear if seen from E? So there is an observer here. To this observer, where will the fish appear to be? So now you know that the rays will come out of the fish is the object, and then these rays will get refracted from this curved surface before they enter into the eyes of the observer placed at E. We know what is the formula. Formula is mu2 by v minus mu1 by u equals to mu2 minus mu1 by r. Mu2 by v minus mu1 by u equals to mu2 minus mu1 by r. The only question is, what is mu2, what is mu1, what is u, what is v, what is r? What will you substitute the value of all of them? So, by using the formula mu2 by v minus mu1 by u equals to mu2 minus mu1 by r, as they have given me both refractive index of first medium, second medium, one is water, one is air. They have given me position of object. They have told me the radius, so I can substitute the distance of the center from the pole, and all I need to find is v. So as to find v, I just need to substitute the value of mu1, mu2, u and r. Now what value should I substitute? As I have got less time, I am taking just one example, and I am taking the example which the students usually do wrong. So now focus here. Where is the pole? The pole is the center of the refracting surface. Here will be the pole. What is the direction of the incident rays? So sir, the incident rays come out of the fish, hits the refracting surface before moving on to E. So from right to left is the direction of motion of incident ray. So this direction will be taken as positive and this direction will be taken as negative. Now kids, tell me, what will you substitute the value of mu1 as? Sir, mu1 is the refractive index of the medium containing the incident rays, and here the incident rays are inside water. So you will say that mu1 is nothing but 4/3 refractive index of water. And mu2 is the refractive index of the medium containing the refracted rays, and the refracted rays are moving in air. So mu2 has to be equal to 1. Air has got a refractive index of 1. So you have established what is mu1, what is mu2. Next question is, what will you substitute the value of u as? The position of object with respect to the pole of the refracting surface. So you will say that here is pole. I have to take the direction of motion of incident ray as positive. This will be positive. What is u? The position of object with respect to pole. Now this direction is negative. Can you tell me what will be this distance? So as in the question they have said that the radius is 10 centimeter. So the center to pole distance is 10 centimeter. And the object is at a distance of 4 centimeter from center. So the distance from pole will be 6 centimeter. So you will substitute u as minus 6 centimeter. And the last thing you need to substitute is r. Now kids, tell me, you will substitute r as plus 10 centimeter or minus 10 centimeter. You will never place it wrong if you know the definition of r. The definition of r is position of center with respect to pole. and center is here, pole is here, and this direction is negative. So you will substitute r as minus 10. And once you will substitute everything in the formula and you will solve, you will get v comes out to be equals to minus 5.2. Minus 5.2 tells me that it is in this direction at a distance of 5.2 centimeter. Now let's move on and start the best topic in the optics, and that is talking about lenses. When we talk about lenses, we first need to understand the type of lenses. So what are lenses? Lenses is a transparent medium bounded by two refracting surfaces. So there has to be two refracting surfaces, and the transparent medium bound between them is called the lens. Now there are two types of lenses we know. There are convex lens and there are concave lenses. But they have got more further subtypes. So what are convex lenses exactly? Convex lenses are the one which are thick in the middle and thin on the side. Thick in the middle and thin on the side. So thick at the middle. To the contrary, concave lenses are the one which are thin in the middle and thick on side. Thin in the middle and thick on side. Those are called concave lenses. Now there are further classification of convex lenses and concave lenses. You can have a double convex lens. You can have a plano convex lens. One side is plane and one side is convex. And you can have concavo convex lens. So one side is concave, one side is convex, but the overall nature is convex. That's why convex is written at the end. Concavo convex lens, overall nature is convex. It is thick in the middle. Now, similarly, we have got multiple type of concave lenses. There is biconcave, double concave. There is plano concave, one side plane, one side concave. And there is convexo concave. Convexo concave. Do you guys know that convexo concave lenses are the most commonly used type of lenses? The type of glasses I am wearing right now, they are nothing but convexo concave lens. If any child is watching this video who wear specs and have negative power, then they must be wearing convexo concave lens. They can take out their glasses, they can touch them. They are thin in the middle and thick on the side. Thin in the middle and thick on the side. Something like this. Now, once we have learned the basic definition of convex and concave lens, to understand the lens better, we should talk about something called lens maker's formula. There are two types of lenses. There are converging lenses, there are diverging lenses. Let's say you have a converging lens, and to explain it, I am taking biconvex lens. If we hit parallel beam of light on this, it's a converging lens. What will it do? It will converge the rays. So after coming out, the rays will be converged and these parallel rays will meet at a point. And this point is called the focus. Now tell me, for a converging lens, the position of focus with respect to optical center will be positive or negative. So you will say, sir, the direction of incident ray is taken as positive direction. For lenses, we measure all the distances from something called optical center. So for a converging lens, the value of f, which is the position of focus with respect to optical center, is positive. And for a diverging lens, if you place a biconcave lens made up of glass in air and you hit their parallel rays of light, what does a diverging lens do, sir? The diverging lens will diverge the rays. So these rays, after they have got diverged, do they actually meet somewhere? No, but their extension will meet. So you will say that these parallel beams, once they have been refracted, they are focused towards the focus. Now, this is the direction of incident ray. So from left to right, you will take positive. So for a diverging lens, the focal length is said to be negative. The position of focus with respect to optical center is said to be negative because you have to move in negative direction. So just remember, for a converging lens, f is positive, position of focus with respect to optical center, and for a diverging lens, f is negative. What is f? Position of focus with respect to the optical center. Now there is something called lens maker formula. The lens maker's formula tells us that the formula goes like 1 upon the focal length equals to the refractive index of the lens material upon refractive index of the surrounding material minus 1 into 1 by R1 minus 1 by R2. So 1 by f equals to refractive index of the lens material upon the refractive index of the surrounding material minus 1 into 1 by R1 minus 1 by R2. Now again, only two things matter here. The first thing, mugging up the formula. I know that most of you already remember this formula, and those who don't, use your photographic memory to look at the screen right now and remember this formula. So 1 by f equals to mu L by mu s minus 1 into 1 by R1 minus 1 by R2. 1 by f equals to mu L by mu s minus 1 into 1 by R1 minus 1 by R2. If you have mugged up the formula, the next thing you need to focus is on the terminology. So first thing, what is f? Sir, position of focus with respect to optical center. For a converging lens, f will be positive. For a diverging lens, f will be negative. So for converging lens, f is positive. For diverging lens, f is negative. You should know this. What is mu L? Sir, refractive index of the lens material. What is mu s? Refractive index of the surrounding material. What is 1? But what is R1? Now, R1 is the position of the center of the first refracting surface with respect to optical center. What is R2? Position of the center of the second refracting surface with respect to optical center. I will explain this more, do not worry, but remember what is 1 by R1 minus 1 by R2. Now let's take a case. Let's say you have a biconvex lens. If you have a biconvex lens, and let's say rays of light hit from the left hand side. So you will say that this is the optical center, yes. The direction of incidence ray has to be taken as the positive direction. Now you can see two refraction will take place, one on the left surface, second on the right surface. For the first reflecting surface, the center is somewhere here. So you will say R1. What is R1? The position of the center of the first reflecting surface with respect to optical center. So you will say for a biconvex lens, R1 will be positive. Now, bacho, what will be R2? When the rays further move, they get refracted from the second surface as well. The second surface can also be assumed to be part of a sphere whose center will be somewhere here. What is R2? The position of the center of the second refracting surface with respect to the optical center. So for the case of biconvex lens, R1 will be positive and R2 will be negative. R1 will be positive and R2 will be negative. So what if they give me biconcave? It's not rocket science, kids. Let's say this is incident ray. Now, R1 is the position of center of the first refracting surface with respect to the optical center. So the center of this first surface will be somewhere here. So you will say that R1 will be negative. So what about R2? Now this is the direction of incident ray, left to right. So this direction has to be taken as positive. The center of the second refracting surface will be somewhere here. Its position with respect to center is R2. So you will say that R2 has to be positive. So for a biconvex lens, R1 is positive, R2 is negative. For a biconcave lens, R1 is negative, R2 is positive. Keep this thing in mind. Now, bachon, you need to understand that if the lens is of denser medium, it means that if the refractive index of the lens material is greater than the refractive index of the surrounding medium, then mu L by mu S minus 1 is positive. I am saying that if the refractive index of the lens material is greater than the refractive index of the surrounding material, then this quantity will be greater than 1. Greater than 1 minus 1 will definitely give you a positive number. And the second case, if the lens is of rarer medium, if the lens material has got smaller refractive index than the surrounding, then lens has got lesser refractive index, surrounding has got more refractive index, then mu L by mu S will be less than 1. And a number less than 1 minus 1 will be negative. So if you have got a lens of glass placed in air, you will say that mu L is 3 by 2, mu surrounding is 1. So mu L by mu S will be 3 by 2, and 3 by 2 minus 1 is half, which is positive. But think of the other case. Let's say inside a glass slab, you have a convex shaped cavity filled with air. So surrounding is glass and this lens is a cavity filled with air. Now you will say that the refractive index of the lens material, which is air, is 1. And the refractive index of surrounding, which is glass, is 3 by 2. Now your quantity mu L by mu S will be 1 upon 3 by 2, that is 2 by 3, and 2 by 3 minus 1 is minus 1 by 3, that will be negative. So if the lens material has got higher refractive index, then mu L by mu S minus 1 will be positive. If the lens material has got lower refractive index, then mu L by mu S minus 1 will be negative. Now beta, remember that I said for a biconvex lens, R1 is positive, R2 is negative. If R1 is positive and R2 is negative, what can you say about 1 by R1 minus 1 by R2? So sir, R1 is positive, R2 is negative, yes. Then 1 by R1 minus 1 by negative number, that becomes 1 by positive plus 1 by positive, that is positive. So understand that for a convex lens, 1 by R1 minus 1 by R2 is positive. For a convex lens, any lens which is thick in the middle and thin on the side, for such a lens, you always get 1 by R1 minus 1 by R2 as positive. And for a concave lens, I told you that R1 will be negative. The position of center of the first refracting surface with respect to optical center will be backward. So R1 will be negative while R2 will be positive. So for a concave lens, R1 is negative, okay, and R2 is positive, okay. So what can you say about this quantity? So sir, for a concave lens, 1 by R1 minus 1 by R2 is negative. So sir, what are you trying to say from here? Think of these 4 conditions. The first condition, you have a convex lens. The convex lens has a refractive index of, let's say, 3 by 2 made up of glass placed in the surrounding of water, and water has got refractive index of 4 by 3. So you will say that, sir, for this particular case, the lens has got higher refractive index, yes. So mu L by mu S minus 1 will be positive. And since you have got convex lens, 1 by R1 minus 1 by R2 will also be positive, and positive into positive gives you positive. So the focal length has to be positive. So the lens has to be converging in nature. Now think of the second case. You have still got convex lens, but this time this convex lens is made up of water. So it has got refractive index 4 by 3. And this water is trapped inside a glass slab. So the surrounding now has got a refractive index of 3 by 2. Now since the surrounding has higher refractive index, what will you say about mu L by mu S minus 1? So sir, mu L by mu S minus 1 will be 4 by 3 upon 3 by 2 minus 1. That will become 8 by 9 minus 1. And 8 by 9 minus 1 will give you minus 1 by 9. So now sir, mu L by mu S minus 1 is negative, but it is convex lens. So 1 by R1 minus 1 by R2 is positive. So mu L by mu S minus 1 for this case will be negative. But since the lens is still convex, 1 by R1 minus 1 by R2 will be positive, and negative into positive gives you what? Sir, negative. So the focal length will be negative, and as the focal length will be negative, it becomes a diverging lens. So a convex lens is a converging lens when it is placed in a surrounding of lower refractive index. A convex lens is a diverging lens when it is placed in a surrounding of higher refractive index. Similarly, I can say that a concave lens is a diverging lens when placed in a surrounding of lower refractive index. And a concave lens is a converging lens when placed in a surrounding of higher refractive index. If you have got a concave lens made up of water, refractive index 4/3, and the surrounding is glass made up of refractive index of 3/2, then when light rays will hit it, it won't diverge. It will end up converging them, and hence its focal length will be positive. So now let's talk about some example. If you have got equiconvex lens, okay, equiconvex lens. Equi word is used when both the radius of curvature have the same magnitude, r and r, equiconvex. We are not saying biconvex, right? We are not saying double convex. We are saying equiconvex. So the radius of curvature on both the sides is c, r and r. And you need to find, let's say, its focal length. So you will say that if light rays hit from here, r1 will be plus r and r2 will be minus r. Because for the second surface, the center will be somewhere here. So the position of center of the second surface will be negative. So r1 will be plus r, r2 will be minus r. Now, if you need to find its focal length, you will use the formula. You will say that 1 by f equals to mu L by mu s minus 1. So let's take the glass material refractive index as mu and surrounding is air minus 1 into 1 by r1 plus r minus 1 by r2 minus r. So this minus minus becomes plus. So you get 1 by f equals to mu minus 1 into 2 by r. So f comes out to be r upon 2 times of mu minus 1. Now once you have found this, in ordinary world, the lenses are made up of glass. So the value of mu is 3/2. So when you substitute in place of mu 3/2, you get that for refractive index to be 1.5, which is 3/2, the focal length comes out to be equals to r upon 2 times of 3/2 minus 1. And with a 3/2 minus 1 is half. So you get r upon 2 into half, and 2 into half is 1. So you simply get the focal length equals to r. So if parallel beam is hit on it, then they will focus at a distance r from the optical center. Let's see next example. If you have plano-convex lens, plano-convex means one side flat, one side curved. So if you have got plano-convex lens, now for this flat surface, a flat surface can be thought of a circle of radius infinity. So you will say that r1 will be infinity. And if the light rays hit from here, then r2 will be negative. So you will write r2, let's say, as minus r. Now using the formula, you will write 1 by f equals to mu L, take it mu upon mu s. We are talking about air, 1 minus 1 into 1 by infinity minus 1 by minus r. So that gives you 1 by f equals to mu minus 1 into 1 by infinity becomes 0, minus minus becomes plus 1 by r. So you get that the focal length, flipping both the side, comes out to be equals to r upon mu minus 1. So focal length equals to r upon mu minus 1. If you substitute mu as 3/2, so for mu equals to 3/2, 1.5, you will get the focal length equals to r upon 3/2 minus 1. So that comes out to be r upon half, that comes out to be 2r. Remember how I said that in case of equiconvex lens, both the surface converges. Now, if you have got a plano-convex lens of same radius of curvature, you can think that you had an equiconvex lens and you removed the half of it. And once you have removed the half of it, now only half part of it is converging. Only half part of it is converging. That's why when parallel rays are hit, they are now getting focused at double the distance. So the rays which were getting focused at a distance r earlier, because of double convergence, are now getting focused at a distance 2r. And this is how I remember many a result, because I keep on attaching sense to it. Moving on to the next case, if you have got equiconcave lens, then beta we know that R1 will be taken as negative, R2 will be taken as positive if we assume the incident rays from here. So you'll say that R1 will be minus R and R2 will be equals to plus R. If you use the formula 1 by F equals to mu upon 1 minus 1 into 1 by R1 minus R minus 1 by R2 plus R. So here you can see that minus 1 by R minus 1 by R, that gives you minus 2 by R. So you get 1 by F equals to mu minus 1 into minus 2 by R. Or you can flip it both the side and you will write F equals to minus R upon 2 times of mu minus 1, or you can write it 1 minus mu, removing this minus sign. So F comes out to be minus R upon 2 times of mu minus 1. Now again, substituting the value of refractive index as 1.5, you will find that F equals to minus R. Substitute it, find it out. And if you have got plano concave lens, now R1 will be equals to infinity, flat surface, and R2, if you assume incident rays from here, R2 will be plus R. And when you substitute it in the formula, 1 by F equals to mu L by mu S minus 1 into 1 by R1 infinity minus 1 by R2 R. This 1 by infinity becomes 0. So what you get is 1 by F equals to mu minus 1 into minus 1 by R. On flipping it, you get F equals to minus R upon mu minus 1. In our everyday life, we use glass lenses, and for glass lenses, refractive index is 3 by 2. So substituting mu as 1.5, we get F equals to minus 2R. Again, for biconcave, we got minus R, lesser focal length. For plano concave, when you had only half of it diverging, you get greater focal length. Now moving on and understanding what happens to the focal length of a lens when we place it inside a liquid and how to find it. So we say that the focal length of a lens in a liquid can be determined by using the following formula. The focal length of lens in the liquid upon the focal length in air is given by this formula. Now sir, where does this formula come from? See beta, if you have got a lens in air and you submerge the lens inside a liquid, what changes? Does the refractive index of the lens material changes? No. Does R1 and R2 changes? No. What changes is the refractive index of surrounding. You can write two equations. One, when the lens is in air, you will write 1 upon focal length in air equals to refractive index of lens upon refractive index of surrounding, which is air, minus 1 into 1 by R1 minus 1 by R2. And once you have submerged this lens inside a fluid, you will say that 1 upon focal length in the fluid, let's call it 1 by FL, focal length in the fluid, equals to refractive index of lens upon refractive index of the surrounding fluid, let's call it L, surrounding liquid, minus 1 into 1 by R1 minus 1 by R2. And dividing them both the side, you will say that FL by FA equals to refractive index of lens, which is written here as refractive index of glass, by refractive index of air minus 1 upon refractive index of lens, which is written as refractive index of glass, upon the refractive index of surrounding liquid minus 1. And this part get cancelled. So this is from where the formula comes. It is nothing but extension of lens maker's formula. Now beta, we need to understand that focal length of a glass lens is 1.5. If let's say the focal length in air for this glass lens is F, then inside water its focal length will be 4F. Sir, how can you say? Check it out. Focal length inside water upon focal length in air equals to refractive index of glass 3 by 2 upon refractive index of air 1 minus 1 upon refractive index of glass 3 by 2 upon refractive index of water 4 by 3 minus 1. So here 3 by 2 minus 1, in the numerator you get half. 9 by 8 minus 1, 9 by 8 minus 1 gives you 1 by 8. And 1 by 2 by 1 by 8 gives you 4. So you will say that the focal length in water equals to 4 times the focal length in air. And that's what this result says. So if a lens has got focal length F in air, then inside water the focal length comes out to be 4f. A direct result you can remember because most of the questions are asked about a glass lens being immersed inside water. The second point you need to understand. In the liquid, the focal length of the lens increases and its power decreases. You say that a lens is more powerful if it can converge better. Think of two lenses, lens 1, lens 2. On hitting parallel rays on both of them, the lens 1 converges a lot and form the image here only. And the lens 2 converges but converges less and forms the image here. Where parallel rays meet after refraction, that is called focus. So the greater the focal length, the lesser is the power of the lens. So do understand that in the liquid, the focal length of the lens increases. And as the focal length increases, it is becoming 4 times. We have just taken one example. So as the focal length increases, the lens becomes less powerful. Continuing and understanding opposite behavior of lens. So in general, refractive index of lens is greater than the refractive index of the medium of surrounding. What we see in everyday life. Lenses are made up of glass and we keep them in the surrounding air, which has got lesser refractive index. So if you have got the lens material having greater refractive index than the surrounding material, then if you have got a convex lens and parallel ray hit them, they get converged at the focus. And if you have got a concave lens and you hit parallel rays, they get diverged. This is what we observe in everyday life. The lens material has got higher refractive index than the surrounding medium. But if you think of a special case where the lens material has got lower refractive index than the surrounding medium, then the convex lens do not converge anymore. When parallel rays of light hit a convex lens, they get diverged. And similarly, if parallel rays of light hit a concave lens, they get converged. Sir, but what if the surrounding and the lens has the same refractive index? From Snell's law, tell me, if both the medium have same refractive index, the light ray will bend towards the normal, away from the normal. That it won't bend. It will neither bend towards the normal, it will nor bend away from the normal. It won't bend because the medium property for the propagation of light remains same. So it goes straight. So as the light do not bend at all, they will pass straight. So if you have a convex lens placed in a surrounding having the same goddammit refractive index, then the rays will simply pass straight. And same is the case for concave lens placed in a medium of exactly same refractive index. Now let's start talking from the basic about lenses. So some definition about the lenses. So if you have got this biconvex lens, the center, this point O, is called the optical center. Whenever we use lens formula, all distances are measured from optical center. Now let's say this left surface is made up of a spherical part whose center is at C1, and the right surface is also made up of a spherical part whose center is at C2. We will say that the line joining C1 and C2 is the principal axis. Now, the line perpendicular to the principal axis is called the optical axis. Now, what is optical center? So we say that the optical center is point for a given lens through which a light ray passes undeviated is called the optical center. So any ray of light which tries to pass through the optical center, that light ray goes undeviated, and this is one important definition that you should know. Now, same type of definitions can be placed even for a concave lens. Now, for this center C1, you will take R1 as positive, and for this center C2, if you assume the incident rays from left, R2 will be negative. And same type of definition for a concave lens. Now, bachcho, moving on, talking about principal focus. There are two principal focus and there are two different definitions for them. There is something called the first principal focus. If you have got whether convex lens or concave lens, the place where an object should be placed so that the image is formed at infinity, that is called the first principal focus. What is first principal focus? the place where the object should be placed so that the final image is formed at infinity. That is called first principle focus. Similarly, we have got a first principle focus for a concave lens. So place where the object should be placed. So you have to place a virtual object in the case of a concave lens. If you hit a concave lens with converging beam, it diverges it. And if after getting diverged, the rays move parallel to each other, this means that the image will be formed at infinity. To get this done, you can't place a real object. You have to use a virtual object. You have to hit here converging rays. So we say that the first principle focus is the place where an object should be placed so that the image is formed at infinity. Now the second principle focus. If you hit parallel rays on a lens, the place where those rays converge is called the second principle focus. So if you have got, let's say, converging lens and parallel rays are hit on it, the place where these rays will converge is called the second principle focus. And when I told you what is F, position of focus with respect to optical center, I was talking about second principle focus. So later when we will learn about the lens formula 1 by V minus 1 by U equals to 1 by F. What is F? Position of focus with respect to optical center. Which focus? The first principle focus or the second principle focus? The answer is second principle focus. Now similarly, if you have got diverging lens and you hit parallel rays on it, they get diverged, right? And they do not get focused at a point, but their extension do. This extension point where you can assume them to be focused or coming out of, that is called the second principle focus. That's why I said that F for a diverging lens is negative. Let's move on and now talk about important points. The first important point, when the medium of the two sides of the lens is same, then F1 equals to F2. This is important. And this is not true just for an equiconvex lens or an equiconcave lens. Even if you have a plano convex lens, let's say you hit parallel beams from this side and you find that these rays converge at a distance of 10 centimeter. Then on the same plano convex lens, if you hit parallel rays from the other side, then they will converge at the same distance of 10 centimeter on this side. So when the medium on both the side of the lenses is same, then the distance of first principal focus is same as the distance of second principal focus. This is what the statement says. Next thing, bachcho, if the medium on the two sides of the lenses are different and they are not same, and let's say on the two sides of the lens, the medium have refractive index mu1 and mu2, and the focal length, the length, only length, magnitude is f1 and f2. Then we say that f1 by f2, f1 by f2 will be same as mu1 by mu2. Or you can say that f1 by mu1 equals to f2 by mu2. Personally, I have mucked it up this way. Why? Because the same logic. If you have a slab of thickness t having refractive index mu, the thickness appear to be when seen from air of refractive index 1 is t by mu. So this slab shifts all things by a distance t minus t by mu. So f1 by mu1 is same as f2 by mu2. Here I am talking only about lengths, not that f, that is the position of second principal focus with respect to pole. Now bachcho, understand that what is focal length? Position of second principal focus from optical center is called focal length. For a convex lens, we have already talked f is positive. For a concave lens, f is negative. And for a plane slab, if you hit parallel rays, it neither converges nor diverges. So it let it go straight. So where will these rays meet? At infinity. So that's why for a plane slab, you will say that f is infinity. Now let's talk about aperture. If you look to the lens from the front, So looking from the front, the lens, like the lens of a DSLR camera, which I'm talking to right now, appears to be a disc, the front part of the lens. Now, the diameter of this lens is called the aperture. Now, how much light will pass through this particular lens through which I'm talking to you? It depends upon the area of the lens. The greater the area of the lens through which the light enters, the more intense will be the image, because more amount of photons will cross it. So aperture is nothing but effective diameter of the light transmitting area is called aperture. Once more, effective diameter of the light transmitting area is called aperture. So if you have ever seen a DSLR camera, the front part is a circle. Now, the effective diameter of the light transmitting area, the light enters through the lens into the camera. So the effective diameter of the light transmitting area is called the aperture. Do understand that the intensity of image depends upon how much light enters, and how much light enters depends upon the area which is responsible for capturing the image. So greater the area, more number of photons will enter into the camera. So intensity of image is directly proportional to area, and area is directly proportional to diameter whole square, as area equals to pi by 4d square. You write it as pi r square. In place of r, you can substitute d by 2. So as the intensity of image is directly proportional to the area, because greater the area, more the number of photons will enter, greater will be the energy of the light forming the image. So intensity of image proportional to area, which is proportional to d square, and d is nothing but aperture. So remember that intensity of image is proportional to aperture whole square. Moving on to more important points. There is something called power of the lens. Means the ability of a lens to converge the light rays. The greater the power, the faster it converges. If you have got two lenses and you hit parallel rays on both of them, the first one converges them at greater distance. The second one converges them quicker. You will say that the second one is more powerful. When I say that second one is more powerful, it means that second one has got lesser focal length. So we say that power of a lens is nothing but 1 upon the focal length of the lens, and the focal length should be substituted in meter. Now in majority of questions you will solve, you will get the focal length in centimeter. So if you wish to substitute here in centimeter, then beta multiply 100 in numerator as well, and you can write power as 100 upon the focal length in centimeter. Personally, I believe that you should stick with the SI unit and here substitute the focal length in meter. As we have learned that for a convex mirror, F is positive, so power comes out to be positive. For a concave mirror, F is negative, so the power comes out to be negative. So when I tell you that I wear lenses of power -4, can you tell which type of lenses I am wearing? Sir, if your lens has got negative power, yes, then the type of lens you are wearing must be concave. I told you at the very beginning of the lecture, the type of lenses I am wearing are called convexo-concave lens. And many of you are wearing them as well. Now, if I say that the power is -4, what is the focal length? So very easy. -4 equals to 1 by f, so f comes out to be -1 by 4, that is -0.25 meter. If you convert it into centimeter, that comes out to be -25 centimeter. So a concave lens of focal length 25 centimeter, the magnitude 25 centimeter. For a plane sheet, as the focal length is infinity, the power comes out to be 0. Now beta, do understand that when you have got thick lens, tell me if you have got thick lens and if you have got thin lens, which one has got greater radius? So sir, thick lens has got smaller radius and thin lens has got greater radius. The formula goes like 1 by f equals to mu L by mu S minus 1 into 1 by R1 minus 1 by R2. For biconvex lens, we will write 1 by r minus 1 by minus r. So 1 by f comes out to be mu minus 1 into 2 by r. So f comes out to be r upon 2 times of mu minus 1. A thick lens has got lesser radius. As the thick lens has got lesser radius, it has got lesser focal length. As it has got lesser focal length, it is more powerful. So thick lenses have got more power, they have lesser focal length, and they have got lesser radius of curvature of the curved surface. To the contrary, if you have got thin lenses, then thin lenses are less powerful. They have less power, they have got more focal length, and as they have got greater radius of curvature. Here, I would like to emphasize on one thing. You might have seen people stressing on their eyes to form an image on the retina. When they do this, they are actually changing the thickness of their eye lens, making it more powerful by compressing it. So when the lens gets compressed, it becomes thicker, its power increases. Moving on and talking about lens formula. Just the way we have learned that mirror formula is 1 by v plus 1 by u equals to 1 by f, there is a formula called lens formula, and in lens formula you just need to remember that there is no positivity, there is negative sign. So 1 by f equals to 1 by v minus 1 by u. Just like when I was teaching you mirror formula, I said that kids, most of the people do not know what is the meaning of u, v and f. They say that u is the distance of object, v is the distance of image, f is the distance of the focus. Do not use these types of terminology. What is u? U is the position of object with respect to optical center. You measure everything for lens from optical center. You treat the optical center as the origin. Now, u is the position of object from the optical center, v is the position of image with respect to the optical center, and f is the position of focus with respect to optical center. Which focus? The second principal focus. For converging lenses, you will get f as positive, and for diverging lenses, you will get f as negative. So moving on and now talking about transverse magnification. In the mirror formula, you get 1 by v plus 1 by u equals to 1 by f. In the mirror magnification, you get minus v by u. In the lens formula, you get 1 by v minus 1 by u equals to 1 by f. In the lens formula, there is no negativity. So the world is balanced. In mirror formula, you get plus. In mirror magnification, you get minus. In the lens formula, you get minus. In the lens magnification, there is no minus. So when we talk about transverse magnification created by the lenses, what is the meaning of transverse magnification? When the object is placed perpendicular to the principal axis. Then the linear magnification is called lateral or transverse magnification. And the formula goes like magnification equals to v by u. After teaching you the magnification for mirror, which I said minus v by u, I said that if the object and image lie on the same side of mirror, u and v will have same sign. And if u and v will have same sign, the magnification will be negative, so the image has to be inverted. Now let's use the same logic but for lenses. If for a lens, the object and image are on same side, then both u and v will have same sign. Either both of them will be positive or both of them will be negative. If the object and image are on same side of the lens, the magnification is going to be positive, and magnification is going to be positive. It means that the image will be erect with respect to object. So if you have a lens and the object and image are on same side, the image will be erect with respect to object. If the object and image are on different side, the image will be inverted with respect to object. And there is no exception to this particular idea. So you need to remember this point as well. Then while teaching you mirror, I said one more thing, that using the mirror formula 1 by v plus 1 by u equals to 1 by f and magnification equals to minus v by u, you can eliminate v here or you can eliminate u here and find two more formulas. The same thing can be done with lenses as well. So since we know that the lens formula is 1 by v minus 1 by u equals to 1 by f, I can substitute v using the formula. or I can substitute u using the formula, and we can even write the magnification as f upon f plus u or f minus v upon f. Once more, revising. If the object and image are on same side of lens, the image must be erect, as u and v both will have the same sign, so the magnification will be positive. If object and image are on opposite side of the lens, the image will be inverted with respect to the object. Because if the object and image are on different side of lens, one of them will be positive, one of them will be negative. So the overall magnification is going to be negative. Now let's talk about longitudinal magnification. If you have got small object and this small object is placed along the principal axis, then how to find the magnification in it? Means how to find the size of image upon the size of object. So we are going to do the same things as we did for mirror. We will say that dv equals to v square by u square into du. Sir, from where do you get this? Very easy. If you write 1 by v minus 1 by u equals to 1 by f, you can rewrite it as v raised to power of minus 1 minus u raised to power of minus 1 equals to f raised to power of minus 1. Differentiating out each term, d v raised to power of minus 1 minus d u raised to power of minus 1 equals to d of f raised to power of minus 1. dv raised to power of minus 1 gives you minus 1, v raised to power of minus 2 dv, minus of du raised to power of minus 1 gives you minus 1, u raised to power of minus 2 into du, and df raised to power of minus 1 is 0, as the focal length doesn't change when you change the object position. When you change the object position, image position changes. The focal length does not change. And we know that differentiation of any constant is 0, so that's why I have placed a 0. So from here you can write minus dv by v square plus du by u square equals to 0. On rearranging, you will get dv equals to v square by u square into du. We have learned the same thing for mirrors. In mirror, there was a minus sign here. Now you can say that the infinitely small length of image equals to the position of image with respect to optical center whole square upon the position of object with respect to lens whole square multiplied by infinitely small length of object. So you will say that dv equals to m square du. Do understand that this m is the transverse magnification, not at all longitudinal magnification. And we can say that the size of image equals to m square times the size of object, but do remember that this formula works only for small object placed along the axis. Once more, what is this m? This m is the transverse magnification for the same position of object. Now using this, I'm going to find the velocity of image in the cases of lens. So now let's talk about velocity of image. Let's say you have got an object which moves perpendicular to the principal axis. So there is principal axis, there is a lens, and you have got an object which has got velocity perpendicular to the principal axis. You know that for such an object, we can say that the magnification is nothing but height of image upon height of object. So can I write that height of image equals to magnification times height of object? And differentiating both the sides with respect to time, I will say that the rate of change of height of image with respect to time equals to magnification times the rate of change of height of object with respect to time. And this rate of change of height of image with respect to time is the velocity of image. And this is nothing but magnification times the velocity of object. So we will say that vi equals to m times v naught. This formula should be used when the object has velocity in the direction perpendicular to the principal axis. But what if the object moves along the principal axis? So let's say you have got this object which is moving with some velocity v naught along the principal axis. Then sir, we know that the infinitely small change in the position of image equals to magnification square times the infinitely small change in the position of object. So as we know that dv equals to m square du, dividing both the side with dt, I will say that dv by dt equals to m square times du by dt. dv by dt is the rate of change of position of image with respect to time. That is the velocity of image. du by dt is the rate of change of position of object with respect to time. So that is nothing but velocity of object. So we say that velocity of image is equal to m squared times velocity of object. So now we are going to talk about the most important thing in this hour. That is the object and image positions for converging lenses. So if you have converging lens, and let's say this is the principal axis of the converging lens, for every position of the object, where is the image formed and what is the nature of the image? And this is important. Here, I'm not going to talk about diverging lenses later. Why? Because converging lenses are the one which are important. And you might think, why again? Because think of the displacement method to find the focal length that is used for converging lenses. Optical instruments, our eye, all these are nothing but converging lenses. So beta, that's why converging lenses are important and you should know every image position for every object position. So we are going to do the same drill. I will recommend you to take a timestamp right now as I'm going to begin it. So as the object moves from minus infinity to minus 2f, object moves from minus infinity to minus 2f. For the object at minus infinity, the image is formed as plus f, because the rays coming and hitting this lens will be parallel rays. For the object placed at minus 2f, the image is formed at plus 2f. You can verify this using the lens formula. As the object and image are on different side of the lens, we will say that the image is inverted. The image is closer to the lens compared to the object, so the image will be diminished. And as these rays are actually meeting, the image will be real. So as the object moves from minus infinity to minus 2f, the image moves from plus f to plus 2f. We can say that object moves faster because object travels greater distance from minus infinity to minus 2f, greater distance. So object travels faster than the image. Image is real because the rays are actually intersecting. The image is inverted. Sir, how do you know? From the magnification formula of lens. The magnification formula for lens gives you V by U. If the object and image are on different side of lens, then U and V will have different sign, but the magnification will be negative, so the image has to be inverted. And the image will be diminished because the image distance V is less than the object distance. So the magnitude of magnification comes out to be less than 1. That's why the image will be diminished. When the object reaches minus 2f, the image is formed at plus 2f. For this extreme case, the object distance and the image distance is same. That's why the magnitude of magnification is 1. So the image has same size as the object. Now let's move the object further from minus 2f towards the lens. As the object moves further from minus 2f to minus f, the image moves from plus 2f to plus infinity. Object placed at minus f. At the position of primary focus, then the rays after coming out will move parallel and they will form image at plus infinity. Since the image distance is very large, magnification will have very high magnitude. So the image will be highly magnified, real and inverted for the object placed at minus f. So as the object is further moved from minus 2f to minus f, the image moves from plus 2f to plus infinity. In this case, you can see that image travels greater distance. So image moves faster. The image is still real. The image is inverted and the image is enlarged as the image distance is more. So object going from minus infinity to minus 2f, image moves from plus f to plus 2f. Object moves from minus 2f to minus f, image moves from plus 2f to plus infinity. Keep on visualizing this. Now once the object has reached focus, the image is at plus infinity. If you move the object further, if you move the object from minus f to optical center, then you do not get any more real image. You get virtual image. And why? Understand this. If you place object very close to the lens, then the rays coming out of the object and hitting the lens will be highly diverged rays. And it will be difficult for the lens to converge these highly diverged rays. It will converge, but might not be able to sufficiently converge to form a real image. So the image formed will be still virtual in nature. So do understand that if the object is placed within the focus between minus f and optical center, then the image formed is virtual. For the object at minus f, the image is formed at minus infinity, just within minus f. And for the object placed at optical center, if you take a lens and place an object very close to it, then this small part of lens acts like a slab and it forms the image nearly at the same position. So as the object moves from minus f to optical center, the image moves from minus infinity to optical center. Sir, why are you drawing erect image? Because now the image and object are on same side of lens. So image has to be erect. Image has to be enlarged because it is at greater distance, and image has to be virtual. So under which condition a converging lens form a virtual image of a real object? To form a virtual image of a real object using a converging lens, the object must be placed between focus and optical center. So when the object moves from minus f to optical center, the image moves from minus infinity to optical center, the image moves faster, the image is virtual, the image is erect because object and image are on same side, and the image is enlarged. Now we will talk about objects which are virtual. Means the object placed between optical center and plus infinity. To get virtual objects, you must hit convergent rays on the converging lens so that the rays do not actually intersect, but their extension does. So for the object placed between optical center and plus infinity, which are nothing but virtual objects, and do understand, to get virtual objects, you must hit convergent rays on this lens. When you hit parallel rays, what does this lens do? So the lens converge them and make them meet at the focus. If you already hit convergent rays, what will happen? Then sir, the lens will converge them further and they will meet even before the focus. So the plus f is somewhere here. These rays will meet even before the focus. And that is something you should know. So for all the virtual objects, for the objects placed between optical center and plus infinity, the image is formed between optical center and plus f. For the virtual object placed at plus infinity, what is the meaning of it? It means that you are hitting parallel rays. So these rays will meet at focus. So as the virtual object moves from optical center to plus infinity, the image moves from optical center to focus. Now in this case, who moves faster? Definitely the virtual object moves faster. So object moves faster. Image is real. So how can you say image is real? Beta, because these convergent rays will actually intersect each other after the refraction. So image is real. So how can you say that image is erect? Because the virtual object and the virtual image are on same side of the lens. That's why they have to be erect. And it will be diminished because the object distance is more and the image distance is less. So you need to know all these points. Now, as I said already, go to the timestamp where I begin and revise it once more. If you remember them, it will help you a lot in understanding optical instruments better. Now it's time to talk about some important points regarding lenses. The first point, this is important. A diverging lens forms virtual image of real object when the object is placed between focus and optical center. So for a converging lens, which is used in microscope, telescope. To form a virtual image, the object must be placed between focus and optical center. The lens forms a virtual enlarged erect image. The second point is important to understand the displacement method. And the second point is the minimum distance between an object and its real image formed by a convex lens is 4f. For an object, when the object moves from minus infinity to minus 2f, the image moves from plus f to plus 2f. Yes, sir. And when the object moves from minus 2f to minus f, the image moves from plus 2f to plus infinity. Now, when is the separation between the real object and its real image is minimum? So the minimum separation between a real object and its real image is 2f plus 2f, and that is 4f. So let's say you have a convex lens, converging lens of focal length 10 centimeter. And somebody said, I placed a real object in front of it at a distance of 5 centimeter. And I find a real image formed at a distance of 20 centimeter. Is this possible? It's not possible. So why it's not possible? Because here the separation between the object and its real image is 25 centimeter. The minimum separation between the real object and the real image formed by a converging lens has to be 4f. If the lens has a focal length of 10 centimeter, then minimum separation has to be 40. It can be 50, it can be 60, it can be 80, but it can't be less than 40. Now, the next point, for all real objects, a diverging lens form virtual, erect, diminished image. So image will be virtual, erect as well as diminished. So why? Let's say beta, you have a diverging lens, a concave lens made up of glass placed in air, and you have placed an object in front of it. So the rays coming out of the object which is going to hit this lens will be diverging in nature. What will the lens do? So it will further diverge them. So these rays will appear to be coming from here. Now this image is which type of image? Sir, it is virtual image, because the refracted rays are not at all intersecting, their extension is. This will be erect. Sir, how do you know? Because the real object and its virtual image are on same side of lens, so it has to be erect. And diminished, why? Because the image will be closer to the lens compared to the real object. That's why diminished. So these are the important points you should know. And the last thing left for this hour is called determining the focal length of a convex lens, converging lens, by using displacement method. And this is important. So how do we use this method? So for two different position of lens, two images of an object is formed at the same location. What? For two different position of lens, two images of an object is formed at the same location. So we fix the object position, we fix the screen position, and then for two different position of lens, we form the image on the screen. Now we know that if you want to form the image of this object on the screen, then the image has to be real. And the minimum separation between an object and its real image formed by a converging lens is 4f. Hence, the separation between object and screen should be kept at least more than 4f. So if you are using a lens of focal length 10 centimeter, then this gap should be more than 40 centimeter. If you are using a lens of 25 centimeter, then this gap should be more than 100 centimeter, greater than 4f. Sometimes this type of question will be asked. If the separation between object and screen is 120 centimeter, and we can't find one sharp real image while moving a lens between the object and screen, then what can you comment for the focal length of this lens? So if you can't find one sharp real image, this means that the D is less than 4f. So 120 is less than 4f, or the focal length is greater than 30 centimeter. So beta, so as to get sharp image of this object on the screen, the distance between the object and screen should be greater than 4f. Now what do? We take the convex lens whose focal length we wish to find and start moving it from object to the screen. And let's say for one particular position of lens, we get a sharp image. Let's say this image is called I1, image 1. Then we keep on moving the lens, and for one more position, we get again sharp image. And let's say for this position of lens, we get an image, and the image is denoted as I2. Now what I want you to focus here is, you are getting for two different position of lens, two different images. Why will this happen? For the simple reason, if you visualize both of them simultaneously, then beta, if this distance is A and this distance is B, when this distance will be B, this distance will be A from the principle of reversibility of light. So when the object is at a distance B and image is formed at distance A, for the object at distance A, the image will be formed at a distance B. Now, once you know the separation between these two positions for which you get the sharp image, you can find out the focal length of this lens using the formula. Focal length equals to d square, the separation between object and screen whole square, minus x square, where x is the distance between the two positions of the lens for which you get sharp image, upon 4 times the separation between object and screen. Now people say this formula is difficult to derive, it's easy. How? Let's say beta, this distance is A and this distance is B. Then for another position, you will say that this distance has to be B and this distance has to be A. So I can say that A plus X plus A plus X plus A equals to the separation between object and screen, D. So from here you get A equals to D minus X by 2. Similarly, we can say that B, this length, equals to X plus A. So if B equals to X plus A and A can be substituted as D minus X by 2, we get B equals to X plus D minus X by 2, that becomes D plus X by 2. Now once you know that A is D minus X by 2 and B is D plus X by 2, using the lens formula 1 by V minus 1 by U equals to 1 by F, you can find out focal length. How? In place of V, you will substitute plus D plus X by 2. So you will write 1 upon D plus X by 2 and the 2 goes up, minus. In place of U, you will write minus of D minus X by 2. So minus of D minus X by 2 and the 2 goes up, and this equals to 1 by F. So from here you get 2 by D plus X, and this minus minus becomes plus, plus 2 upon D minus X equals to 1 by F. If you multiply these terms, so you will get 2D minus 2X plus 2D plus 2X upon D square minus X square equals to 1 by F. Cancel out this minus 2X plus 2X. So you get 4D upon D square minus X square equals to 1 by F, and on flipping both the side, you will get F equals to D square minus X square by 4D. So should we remember this formula? Sure, this is important result. So the focal length is D square, the separation between object and screen whole square, minus X square, the separation between the two position of lens for which you get sharp image, upon 4 times the distance between object and screen. There is one more thing. If for two position of lens, the images have size I1 and I2, the length of image is I1 and I2, then you can say that the size of the object will be the geometrical mean of the length of the two images. So the length of the object will be equals to root I1 I2. Sir, how can you say? if beta I take this distance as A and this distance as B. So I know that magnification will be equals to V by U. So plus B upon minus A for the first case. So magnification for first case will be equals to I1 upon the length of the object, and this will be equals to B by A. For the second case, this length is B, the object distance is B, and the image distance is A. So for the second case, I will write magnification as image distance, which is plus A, upon object position, which is minus B. So you will write I2 by O equals to A by B if we just talk about the magnitude. So I1 by O equals to B by A, I2 by O equals to A by B. So if you flip the second equation, you will say that A by B equals to O by I2, or you can say that I1 by O equals to O by I2. Cross multiply, you will get that O square equals to I1 I2, or the length of the object is nothing but under root of the length of the two images. So size of the object equals to root I1 I2. So that's all in this hour. In the next hour, we will talk about the combination of lenses with mirror, and we will talk about prisms. See you guys in next hour. Bye bye. So that's all for now. See you guys in the next hour.